Good evening, all. This is my 18th video lecture. 18th video lecture. So today I'm going to discuss the numerical problems, some more numerical problems on steady flow energy equation. Some more numerical problems on steady flow energy equation. So these are the exercise problems from the Pekenag textbook, right? So here it is given that a blower handles 1 kg per second of air at 20 degrees centigrade and consumes a power of 15 kilowatts. The inlet and outlet velocities of air are 100 meters per second and 150 meters per second respectively. Find the exit air temperature. So here find the exit air temperature assuming the adiabatic conditions. Take Cp of the air 1.005. So in thermodynamics, some of the things you have to see that. So whenever you are going to write the expression, that is PV to the power of gamma is equal to constant. PV to the power of gamma is equal to constant. So this gamma is nothing but adiabatic index, or this is nothing but isentropic index, right? So that is, this gamma is nothing but equal to Cp by Cv. So gamma for what type of a gas it is. So that is gamma for monoatomic gas. Gamma for monoatomic gas. That standard value you have to use it as a 1.67. For the diatomic gas, so monoatomic gases means here you can take it as a helium, neon, monoatomic gas. So diatomic gas means where you can take it as a nitrogen, oxygen. So the value which you have to consider as a gamma as 1.4. Next, gamma for triatomic gas. Triatomic gas. So this gamma value for the triatomic gas, it is around 1.27 to 1.3, right? The example for this particular case is carbon dioxide, nitrous oxide, right? Gases. So the triatomic gas, it is 1.27 to 1.3, but for diatomic gas it is 1.4, and for monoatomic gas it is 1.67, and the gamma for air, the standard value, that is the gamma for air, it is 1.4. And some of the things you have to remember that Cp for air, that is Cp for air is to be considered 1.005 kilojoule per kg Kelvin. Next, Cv value for air. Cv value for air, it is 0.717 kilojoule per kg Kelvin, right? And some of the things that that is R is equal to, this is the gas constant, difference between the specific heat at constant pressure and specific heat at constant volume, right? And the another that is when you are going to write this, Cp is equal to, right, gamma R by gamma minus 1. Cv is equal to R by gamma minus 1. So these are the things that you have to get. Now here blower, that is air as a working fluid. So when air as a working fluid, then gamma is 1.3 to gamma as 1.4, Cp standardized value is 1.005. But here the value is given, but sometimes they won't give these particular values. So that student has to observe. Cv for air, it is 0.717 kilojoule per kg. Next, R value is also there. So this R value is a standard value. It is 0.287 kilojoule per kg Kelvin. 0.287, right? Or it may be the 287 kilojoule per, sorry, it is joule per kg Kelvin. 287 joule per kg Kelvin, right? So it is joule per kg Kelvin, right? So these things. Next, the gas constant. Other sometimes other than the air is going to give. So that gas constant R is equal to that. It is written as universal gas constant divided by molecular weight of that particular gas. So the universal gas constant is taken as 8.316 kilojoule per kg Kelvin. 8.316 kilojoule per kg Kelvin, right? Or it is 8316 kilojoule per kg Kelvin. Molecular gas, say suppose if it is hydrogen gas, molecular weight is 2. If it is a helium gas, molecular weight is equal to 1, right? So that is if it is a molecular weight for carbon dioxide, that it is 44, right? So this is how you have to take considerations while solving the numerical problem. So before going to solve the numerical problem, so these are the things where a student has to keep it in mind for the thermodynamics point of view. Now coming to the problem here, the blower is given. Blower is mentioned here. Blower means, it is a, here certain things you should have to observe in thermodynamics. Then there is a blower is there, fan is there, and compressor is there, right? So the difference between the fan is to blower is to compressor, right? Compressor. So in all the cases, the pressure ratio, that is outlet pressure by inlet pressure. So here also the blower P2 by P1. In a compressor, the pressure ratio P2 by P1. So all this you can call it as a pressure ratio. Pressure ratio, that is PR, pressure ratio. So for a fan, the pressure ratio is equal to 1. For a fan, the pressure ratio is equal to 1. And the blower, normally it is around 1.2 to 1.3. And for the compressor, it is more than the 2. For the compressor, it is more than the 2. There are the different types of compressors are there. So while dealing this particular thing, mechanical systems, then you can come across. But in all the cases, the pressure ratio is important. So the fan, for the fan, the pressure ratio, that means the pressure ratio means for a fan, that is the P2 is nothing but equal to P1 because it is 1, right? P2 by P1, that is equal to 1.2 to 1.3 for a blower. That means the outlet pressure is 1.2 to 1.3 times the inlet pressure. The outlet pressure is 1.2 to 1.3 times the inlet pressure. And the compressor, the outlet pressure divided by inlet pressure, which is nothing but 2 times the inlet pressure. So these are the certain things that student has to observe in this particular type of thing. So here the blower problem is given. So the blower problem means now the pressure ratio it is around that is which it is greater than 1.2 to 1.3. So first thing is drawing the blower, right? So how you can draw the blower? So just blower is nothing but here. So this here when you right, so completely you are here giving the to this one. So here you are giving the work input to this one, that is d bar w by dt, d bar w by dt. And if it is insulated, if it is insulated, see, this is the insulated part. If it is insulated, if it is insulated, then how you are going to solve the case, right? So what are the given conditions? So first thing is mass flow rate is given. So that is mass flow rate. It is 1 kg per second, and the temperature is given as 20 degrees centigrade, and consumes a power. That means work input is required. So consumes a power of 15 kilowatts. The inlet and outlet velocities of air. So the inlet velocity, that is C1, is 100 meters per second, and the outlet velocity, that is 150 meters per second. Find the exit air temperature, assuming the adiabatic condition. Find the exit air temperature. So how you are going to find out the exit air temperature? The mass flow rate is given. So what is the steady flow energy equation you are going to write? So the steady flow energy equation, it is m1 dot, because it is enthalpy, that is h1 plus c1 square, because it is you can write it as c1 square divided by 2000, which are in kilojoules. Next, gz1 divided by 1000 kilojoule per kg, right, plus d bar q by dt is equal to m2 dot h2 plus c2 square by 2000 plus gz2 divided by 1000 plus d bar w by dt, d bar w by dt, right, d bar w by dt. Then here the potential energy terms are the potential energy terms, this is 0, and because of insulation this is also 0, this is also 0, right, and these are the given input condition. And anyway, mass flow rate, so that is mass flow rate m dot is equal to m1 dot, that is equal to m2 dot, right. So this is the given expression, right. Now how you are going to solve after taking this particular thing, then after using this particular point, that is the steady flow energy equation, once after using this steady flow energy equation, then you will get it as, let me erase. So after substituting this relation, that is the steady flow energy equation for the blower, for the blower, then what you are going to get? So then you will get it as, when you use this particular formula, that is h1, that is what it is to be calculated. Next, c1 is given as 100 square divided by 2000 plus potential head, it is 0, and the heat transfer, that is also equal to 0. Then the outlet part, that is h2 plus c2 square, it is given as at the exit side, it is 150 square divided by 2000 minus 15 because here the work input is required. Here this is nothing but the work input. That's why it is minus sign. Work input is required. So with this case, that is when you make a calculation, that is H2 minus H1, after making the calculation, you will get that particular value as 8.75. Then what is this H2 minus H1? That is and change in and that is enthalpy is a function of temperature. So T2 minus T1, that is equal to 8.75. Then you will get that is T1. So that T1 is given as a 20. T1 is given as a 20 degree centigrade. So that is T2 is equal to 8.75 divided by this Cp value, it is 1.005 plus 20. This is the 20, right? So you will get the T2 value as 28.7 degree centigrade. 28.7 degree centigrade. So the student has to calculate that is applying the steady flow energy equation. What are the terminologies are there? Then what is meant by enthalpy? Enthalpy is nothing but it is a function of temperature. So related to that one, you need to find out the enthalpy. So this is the answer. This is the answer. Hope, right? Next one is going for the another problem. So look at the another problem, that is here the turbine is mentioned. Here the turbine problem is mentioned. A turbine operates. See, observe the problem. A turbine operates under steady flow conditions, receiving the steam at the following state. Receiving the steam at the following state. That is pressure is 1.2 megapascal. Temperature is 188 degrees centigrade. Enthalpy H1 is given. Velocity is given. Elevation is also given. The steam leaves the turbine at the following states. Pressure is given, enthalpy is given, velocity is given, elevation is 0. Heat is lost to the surroundings at the rate of 0.29 kilojoule per second. If the rate of steam flow through the turbine, that is the m dot is given, rate of steam flow through the turbine, it is 0.42 kg per second. What is the power output of the turbine in kilowatts? What is the power output of the turbine in kilowatt? So first thing is drawing the diagram and sketch, that is important for the steady flow energy equation. So this is how you have to draw the diagram and sketch. And this is the inlet, this is the inlet, and this is the outlet, and this is the power output. You can get it from the turbine. That is the power output getting from the turbine. So the section, that is the inlet section, this is the inlet section, that is 1 and this is the exit section, this is the 2. So here it is given as the pressure, that is the pressure is equal to 1.2 megapascal, and T1, that is the temperature is also given, it is 188 degree centigrade, and the enthalpy, so that is the enthalpy is given as 2785 kilojoule per kg, and the velocity, that is the C1 is given, it is 33.3 meters per second, and Z1, that is this Z1. So if you take the reference section, right? So from this case, the inlet section, this is nothing but the Z1. So that is Z1 is 3 meters, right? Z1 is 3 meters. This is how the things are given, and this is the outlet section. but for the outlet, the the exit section, that is here, this is Z2 is equal to 0. Z2 is equal to 0, right? So this is the datum head. Z2 is equal to, so Z2 is equal to 0, and again here also write down the pressure. What about the pressure at the leaves the turbine at the falling state, that it is 20 kilopascal, and the temperature 20 kilopascal, and enthalpy is given, that is H2 is 2512 kilojoule per kg. Velocity is 100, that is C2 is 100 meters per second, and the elevation is 0. So heat lost to the surroundings. So this is the heat loss, right? So that is equal to 0.29. When the heat is leaving from the system, it is a negative sign. So later we can put it here, but heat is leaving. The direction is shown already, and the power output of the turbine is in kilowatts. So the answer you have to get it is this one. So how you are going to solve this one? That is the mass flow rate. It is given as a 0.42 into H1. What is the H1 value? It is 2785. H1 value is 2785 plus the C1 square by 2000. C1 is, it is given as a 33.3 square divided by 2000, right? Plus GZ1. G is nothing but 9.81 into 3 divided by 1000 and heat is leaving, so it is minus 0.29 is equal to, then again at the outlet point, that is a 0.42, here the steam is going to leave, that is a 2512, and the exit section, the kinetic energy, that is here, it is 100 square divided by 2000 plus the Z2 is 0, and now you have to calculate the d bar W by dt, So after making this calculation, then you will get d bar W by dt from this numericals. So it is the answer is 112.5 kilowatts. 112.5 kilowatts. So try to check the answers with your calculator also. Okay. So this is the second problem. And this is how the student has to solve, that is applying the steady flow energy equation at the inlet and at the outlet point. Then checking the energy balance, drawing the diagram and sketch. What is the inlet section input variables? What is the outlet section output variables? So whether the heat is leaving or heat is entering into the system, and work done by the system or work doing onto the system, these are the things that you have to get in your mind when after applying the steady flow energy equation. So this is all about the second problem. The